Yeah, thanks. Really, it's really nice to be back here. Yeah, so I'm going to talk about quiver folding. We're going to have some quiver with an automorphism, and I want to understand how this interacts with an algebra structure that you can build in a wide variety of contexts, called the cohomological Hall algebra. So a brief plan for what we're going to do is first we're just going to talk about like background on CoHAs. So we have this main construction, which gives us a module for the CoHA, and we need to kind of understand the context for that construction. Then we're actually going to see the construction of modules using automorphisms. So if we have an automorphism, which is kind of an algebra automorphism that comes from geometry in a certain way, we're going to be able to find a really general construction of modules out of this. And then we're going to see some examples, maybe with applications to the AGT correspondence in classical types. So this is basically what we're going to do. Everything that I'm going to talk about is joint with Alyosha Latintsev in this long paper that we posted to the archive this year. So yeah, let's get started with just the setup of cohomological Hall algebras. So how do we get one of these? And our setup is we're going to take A, which is an abelian category. It can't be any abelian category. It needs to satisfy some properties that we're going to talk about. What we need from this abelian category, but some examples that we could get are the category of representations of Q, where Q is a quiver with some edges and some vertices. The other thing we might take is coherent sheaves on X, where X is a, say, smooth, proper, or at least proper enough curve, surface, or Calabi-Yau threefold. And another case that's really interesting, which is related to this geometric case, is if we take a heart of an abelian category, a heart of a T structure in the derived category of coherent sheaves on X, where A is some heart, so some other abelian category that we can see in the previous examples. And I've given you an abelian category, and I want to construct an algebra out of it. So we're always going to need geometric representation theory, some space, and maybe the cohomology of that space of some flavor in order to get a vector space. So M is going to be the moduli stack of objects in A. Some complicated stack. In general, it really is very, very poorly behaved. And then we're going to need a cohomology theory. And sometimes It's going to be just ordinary equivariant cohomology, maybe Borel-Moore homology, maybe critical cohomology, depending on context. So I'll say in words, basically if we have a quiver and not its double, we're fine to take smooth ordinary cohomology. The same works if we take a smooth proper curve. But if we're going to do something like a Calabi-Yau threefold, we're going to need a more sophisticated cohomology theory, like equivariant cohomology. And our result holds in all of these settings, so that sort of works in these three different contexts for Calabi-Yau folds, curves, quivers, surfaces. And we need some axioms in order to get the algebra. And I'll explain basically what we need to have happen in order to get an associative algebra. And it's basically going to be that the following diagram needs to give us an algebra structure. So we're going to let SES denote the stack of short exact sequences where each EI is in our abelian category. We get a correspondence diagram from the stack of short exact sequences where in the left-hand map, we just take our short exact sequence, 0, E1, E2 to E3, map it to the first and third factors. Then on the right-hand side, we have the map that sends it to its middle factor. So it's more or less an extension diagram. We can think of it as a diagram that lets us take two objects and sort of sum up all the way of extending them to form a larger object. And definition, which it's going to be impossible to list the total number of people that have worked on this construction, but a lot of people attribute this to Kontsevich-Soibelman, which is if we take the cohomology of M and our product is given by just P pullback and then Q push forward, is the cohomological Hall algebra of A. And basically, we just need this to make sense. So in all of the axioms we need on our abelian category and cohomology theory, we need to be able to pull back along P and push forward along Q. And that together with standard things that happen in cohomology, Kuna theorem, smooth proper base change, gives us an associative algebra structure on the cohomology of the homogeneous stack. So let's see, some example of why you might care about this. If we take Q as a quiver, and then A is equal to pi Q mod. So here pi Q is the pre-projective algebra. Which is just a generalization of like the cotangent stack, the cotangent abelian category of representations of half of the quiver. So in Nakajima's story, this is the algebra you get by like doubling a quiver and taking a moment map, taking some sort of cotangent bundle. Then it's recently a theorem with two different proofs of by Bode-Davison and Schiffman-Wasserow. Which says that the CoHA of this algebra is isomorphic to the positive half of the Molekukun-Kavianian so somehow we're seeing like positive halves of some quantum groups using this geometric construction, where this is some off algebra, which is a priori defined in a very different way. So the next piece of information that's going to be really important to us is, I've given you an algebra structure, a way of taking two cohomology classes, doing some sort of geometric correspondence to multiply those two cohomology classes. Cohomology class in the first factor here, cohomology class in the second factor here. We get another cohomology class, which is their multiplication. The next piece of information we want is that this is a Hopf algebra, which means not only does it have an algebra structure, it has a coproduct, and an antipode and all this sort of thing. We're really going to be actually concerned with primarily with the coproduct. So an important fact is that I've set up a very general context, so I have to say sometimes, but in all the cases that we care about, the CoHA has a localized bi-algebra structure. And it's an informal seminar, so I'll give you the way you want to actually think about the coproduct. So in the Yangian case, this is the Drinfeld coproduct. So if you're used to working with Molekukun-Kavianians, this is not actually the one that you want to use. But on the other hand, it's the structure that exists in this extremely general setting. And we just define the coproduct by the following formula. So our coproduct, we want to take a cohomology class on M and get, so it goes from cohomology of M to cohomology of M, maybe tensor cohomology of M. And all we're going to do is read our diagram backwards. So we're going to take Q pullback, we're going to take P push forward, and then for kind of funny reasons, we want to swap the two factors and add a plus or minus sign. And this defines a map that goes from the cohomology of M, the tensor product of two copies. The only problem is that, it's basically never going to be the case that we can actually push forward along P because that's like a vector space. And so we need to localize or add some sort of terms in the denominator to sort of push forward and localize cohomology. If that's not something you're familiar with, we just have to kind of invert some elements, and then this gives us some sort of formal operation that kind of goes the other way from a multiplication. Yeah, please do, please do.
So what height of Q is
just a circle node, and then you have no arrows at all. So we're not do you want the pre-projective? Let's do the pre-projective example. Then you get the positive half of the Yangian of SL2. So let's write this example here. So let's take Q is actually just this quiver. Then the cohomology of M is, in all finite ADE cases, we're going to get the Yangian of the corresponding finite ADE type. So this quiver is a type A1 quiver. And so we're going to get the Yangian. Yeah, so here, these are in the same example. So here M is the disjoint union of all dimension vectors of, when we want to say that it's just the stabilizer of this point. And so it's kind of like point modulo GLD, so this sort of stack quotient. But we really want to kind of secretly keep track of the moment map, which in this case looks like it doesn't do anything because it's a function on a space. But if we're going to keep track of some sort of derived structure in the derived zero locus of this map, then maybe it sort of does something. So yeah, so it's just the quotient of the zero locus of the moment map by the corresponding stack, and the algebra is the positive half of the Yangian of SL2, which is some filtered deformation of the universal enveloping algebra of maps from a single variable into the nilpotent subalgebra of SL2. So the total Yangian of SL2 has a triangular decomposition, loops into EF and H, and we only take the positive. So this is passing to some associated gradient filtration. Yeah, in this case it's commutative, right? Because the nilpotent algebra of SL2 is a commutative algebra in one variable, so it's polynomial. And so in this case, actually, yeah, it's the symmetric algebra on a polynomial algebra, and then we have some sort of filtered deformation.
Will that look at the degree D component, cohomology of that?
So at least after we localize everything, and we're going to localize everything here. So the cohomology of M, at least localized, is equal to our disjoint union becomes a direct sum of D greater than or equal to 0. And then it's GLD times torus equivariant cohomology of a point. So we maybe have some extra torus variables that we're throwing in for fun. And then we take GLD equivariant cohomology of a point. Localize. If you're not willing to localize and you really want to care about the integral structure, some sort of funny stuff happens with, you have conditions of like, in this ring, what's the subalgebra of things that don't come from localized? And we're going to avoid those questions, but not because they're not interesting. It's just a little irrelevant to what we're talking about. Yeah, so this description actually lets us give a kind of fun, extremely explicit formula for the algebra. So now is a kind of reasonable time to talk about this. In the case when we have a quiver, we have a shuffle algebra realization of our CoHA. And it just uses a generalization of this observation. So since, and let's just write down the full generalization. So M is a disjoint union over D. And these are just our possible dimension vectors of our quiver, which we can think of them as positive integers for every vertex in our quiver. And then we're going to have this thing that we'll call rep QD, which is a vector space of just arrows in the quiver. And then we'll take the stack quotient by the product over all vertices of GL DI. And at the level of cohomology, we don't care at all here what the vector space is, because we're still just going to get the cohomology of G equivariant cohomology of a point. And we get an isomorphism of cohomology of MD is just, T times GLD, call this product GLD, T times GLD equivariant cohomology of a point, which are just symmetric functions in some number of colors of variables. So we have x1, 1, all the way up to x1, d1. And then in our other colors, we're going to have xn to xn dn. And they need to be invariant under sim d1 times sim dn. So if we only have one vertex, this is just symmetric polynomials in that number of variables. And then I'm telling you that we have an associative algebra structure. So we're going to be able to take two symmetric polynomials in two potentially different sets of variables and take the product. And there's kind of one thing that you could expect that it is we just take the product of the two and multiply them. So if we have f, which lies in cohomology of M degree D, G lies in cohomology of M degree D prime, then we want to say that f of x in our first sets of variables, then star f in G in our second set of variables. This is basically the only thing that you can do to get something symmetric, is we're just going to symmetrize the product f of x1 times g of x2, and then we actually have to then multiply by some rational function zeta in our two sets of variables x1 and x2. Yeah? It's something that maybe acts as a group of automorphisms of the quiver. So in the cotangent case, we're going to have one variable that kind of scales the cotangent direction. And if we have a bunch of edges that go from one space to another, we might add an extra torus that acts as the maybe general linear group on the edge multiplicity space.
So it's not a subgroup of children.
No, it's a group of automorphisms of the entire thing.
Not of the quiver, but of everything I get. Okay, and I guess I'm not sure, but I might have led to confusion for other audience members. And rep QD, probably the D is supposed to stay rep.
You can.
Third row on the right side.
Yeah, you can put it there. You can think of it. Yeah, it's not a different quiver, so yeah, either parentheses around the entire thing or rep DQ. Either one is.
So I get this right that this invariant cohomology is just invariant functions kind of inflated by.
Yeah, it's invariant functions on the group. Yeah, because whenever you take for a reductive group, G equivariant cohomology of a point is just equivariant functions, which are like symmetric polynomials in the maximal torus under the Weyl group. Zeta, yeah, I'll write it down. It's some rational function, and basically it comes from calculating this push-pull diagram using localization. So I think it's better to just write it down in an abstract form. So the SL2 case, it disappears if you don't study it equivariantly, or at least it just turns into a plus minus. So the simplest case that you want is actually passing to this associated graded for SL2. Then up to plus minus, you see no factor at all. And it's literally just that multiplication, which is why it's commutative. So you already made this observation that when that n is commutative and u is commutative, and you have just a commutative algebra. And that's exactly this algebra when there's no zeta and you only have one node. So that is the simplest case. And then this is some sort of adding the zeta deforms things in some sort of funny way. So if zeta of x1 and x2 so this is a rational function in these variables, and it's just the Euler class of the like xed complex of A with B, where A is the universal object in MD, B is the universal object in M. D prime, so it's some localization factor, which just gives you, you take its character in the equivariant cohomology of a point and it gives you some sort of rational function. It's a very general thing. Of course, it depends on the quiver, so you're going to get numerator and denominator factors depending on this. But, it's not going to be helpful. We're never going to actually really use the formula to explain what's going on. Some of our proofs use it, but it ends up being kind of complicated to prove anything using the shuffle algebra formula. So it's good to know that it exists, but it's pretty painful to use in practice, I would say. The coproduct structure is sort of just as complicated. And it's basically, the coproduct structure is more or less, you just read this the other way using 1 over zeta. So it's basically just as complicated. We take a function of n variables and we sum up all the ways of splitting it into 2 sets of variables and multiply by, like, it's not, I guess it's not 1 over zeta, it's zeta of x1, x2 divided by zeta of x2 over x1. And then that's our coproduct. And it's kind of, not any easier, but also not that much more complicated. So there's a trade-off. Yeah, that's sort of what. Yeah, I'm going to talk about that right now. Yeah, so there is geometry, and there's no geometry about the coproduct beyond the same product. You read it the other way. I think. Yeah, that's how I think about it. Yeah, it has this uplift to this joist. So there's a way of taking it and getting a vertex algebra structure out of it, but it really is just you read. It's the geometry is. It's pretty much you read it the other direction around. And then okay, so now I've given you two maps. I mean, Drinfeld was writing about the same coproduct in the 80s, right? So to say, I mean, okay, so I think you see the same coproduct in all these papers of like Fagan and collaborators, except they they're clearly aware of the geometry. You know, like they write representations on like plane partition representations or things like this, except they don't really kind of like say that they're using it. So I think I think people have been using this to productive effect for yeah, at least since certainly before Joyce in a different language.
But not the geometry. Using it in the algebra.
Yeah, to try to understand the algebra. Yeah, and now there's all these wall crossing applications that really sort of find that this coproduct is the fundamental thing controlling wall crossing invariance. Yeah, I guess it really takes like this Joyce realization that this coproduct controls wall crossing invariance for it to have sort of more geometric applications.
The relationship between coproduct.
Yeah, somehow the relation between the localized coproduct and the Joyce coproduct, it seems sort of simple. Like you expand all of your variables, you add plus z to each of your variables and expand in z. Somehow, this doesn't seem like much, but if you're trying to control wall crossing, is some sort of extremely fundamental thing. Yeah, I mean, it'd be great from my perspective. It would be great to actually have the full coproduct. So I see this coproduct as a very degenerate limit of the Mollica-Grunfeld coproduct. So I want a coproduct where I don't have to localize things. And for the stuff that I'm going to talk about today, sort of uplifting to like classical type structure groups, I don't know how to do the full story, and so this sort of simple piece of the full structure is kind of all that I have access to. So I see it as kind of like the first order step to like getting it at the actual coproduct that we want. Which, yeah, I mean, that's a biased perspective because I'm not so interested in wall crossing, and so it's yeah, let's talk a little bit more about this sort of compatibility. So far I've given you two maps and I've said nothing at all about sort of how they're related. And there's actually a really kind of funny structure about how the two are related. So to understand the like bi-algebra axiom, which says that the product and coproduct are compatible, and geometrically, we want to draw this as the following, right? We want to say that we take the product and then the coproduct. This is the same thing as we do this sort of funny operation. This takes place. I'll explain this diagram in a sec if you're not familiar with this. This takes place in a braided monoidal category. Yeah, let's explain these diagrams on the board and then talk about like what is this compatibility relation between the product and the coproduct. And I'll just give you the definition. Hopefully you've seen this before. We're going to generalize it a bit to a sort of weirder situation you may not have seen, so I'll remind you for that reason. So C is a K-linear braided monoidal category if it comes equipped with functor, takes two objects, spits out another object, and then we also want a braiding, which is an isomorphism from A tensor B to B tensor A, which satisfy relations. Most importantly, we want the Yang-Baxter relation for the braiding to be satisfied. So we want to say if we take a triple product of braids, that we can do it in the opposite order and get the same thing. And maybe now is a good time to explain the notation of these string diagrams. So where if we have two objects, A and B, we represent objects as strands or like ends of strands, morphisms as like lines going from top to bottom. And juxtaposition is tensor product. Our braiding morphism beta is here. And if we have A and C is like bi-algebra object, we're also going to have multiplication maps that go from A tensor A to A. So this is going to be some multiplication. And then co-multiplication goes from A to A tensor A. And then a bi-algebra object is one where all of these are compatible via this diagram. So we multiply and then co-multiply. It's the same as doing this sort of funny thing. On the other hand, you should notice that in order to write this down, we've had to sort of switch the strands across each other, which means that the braiding here is used non-trivially in the compatibility axiom for the product and coproduct. So what is this going to be in the case of A is representations of a quiver? Well, beta, well, actually, I'll write the category first. So category is in the representations of a ring called lambda. And then lambda is something like the product over V, which are vertices of our quiver. And we just want to take the universal tautological ring. So anything that we can get as a universal ring that acts by these xi parameters. So we'll write that as GL infinity V, equivariant cohomology of a point, maybe still with a torus. Because that's a big tensor product. Yeah. It's the big tensor product of cohomology rings where we have just infinite symmetric polynomials in one variable for each of the nodes of our vertex. Just our base ring K is T equivariant cohomology of a point where T is some symmetries of the theory. So in the Yangian case, it's going to include this H bar. In other words, you can think of it as T equivariant cohomology of GL infinity that we care about. So yeah, I just want to keep these. I see. So T is equal to like symmetries, the reductive part of symmetries of quiver. So for example, if Q is like a doubled type A quiver, then we're going to, let's say, have T1 that acts scaling our half of our quiver, and T2 that acts scaling the other quiver. And T is equal to like C star T1 times C star T2. And you can just always think about this example. Maybe if you want to throw in some extra like symmetries, you have like edge multiplicity, you can do that. But yeah, basically just some sort of extra parameters that, yeah, if you want to do this deformation, you kind of have to add in some extra parameters. Right, and then so we have some sort of base ring, and then we're just taking infinite symmetric polynomials, those variables, and how does it act on the CoHA? Well, we just forget all of the variables above a given degree, and it just acts by cut product. So we get a different GL for each vector space. Yeah, and then so we're sort of just keeping track of kind of extra stuff. So certainly, like, we still get a representation of T times the product of GLs. It factors through quotient. If we keep track of both T1 and T2, then there is actually extra information. But one of the C stars that sort of scales everything, so that the character, I think, T2 minus T1, I think, is already the central part of the GLs. So you can ignore that if you want, but there is something extra. There's at least this like T1 plus T2 that we sort of don't see that gives us a real deformation. Great. Right. So this is our category, and then I want to give you a tensor product. T is global. T is global. Yeah, we have. T equivariant cohomology of a point. This is the tensor product's taken over the base ring K, which is T equivariant cohomology of a point. Yeah, our base ring in this entire story and all tensor products are always going to be taken relative to that thing. Yeah, so for each vertex, we're going to get symmetric functions in an infinite number of variables that don't symmetrize with respect to each other. So the infinite limit of this, and of course it acts via all of these just by cut product killing of all the extra variables that we don't see. And then we get a braiding. So tensor product comes from, well, I want a bialgebra structure on lambda. And we get lambda goes to the tensor product of two things, maybe with a completion, is pullback along this direct sum map that goes from T times product over all vertices B GL infinity V product squared to the same product. Where we just take the direct sum of, say, like infinite dimensional vector spaces at each node. This formally gives us a coproduct structure. You really want to think of this as like an infinite limit over n. But this is just the usual coproduct on the ring of symmetric functions and various variables. This has a product in coproduct structure, which is just the infinite limit from the cohomology of classifying spaces. So that gives us our tensor structure. And then the braiding, it's basically the swap, but we get a funny localization factor, which is given by this more or less the Euler class. So we can invert the braiding, but we're starting with just sort of one, and so it's invertible. So it's just yeah, it's this diagram and then that's braiding inverse. So we're assuming it's an isomorphism. So this isn't the I'll try to write down like it's just the diagonal part of the usual R matrix. So I'll write down our braiding. It's again we're gonna have maybe a plus or minus, and then we're gonna have the swap, and then it's cut product by this class. So an Euler class of the X class A with B divided by the Euler class of the X complex of B with A dual. So remark, if our Mollica-Kunkov OR matrix, if we take its like LDU decomposition, then beta composed with swap is at least morally equal to just the diagonal part of the R matrix. So, and this is kind of what I said by like, I wish I actually had the full coproduct. I wish I was able to like write down the right braided monoidal category with the full non-localized coproduct whose braiding is given by LDU. But all we're sort of finding is this diagonal part. So I don't really know about unitarity. I mean, I think this is like kind of non-trivial. It's inverse. I don't think so. Yeah, I don't think they're the same. Yeah, I think they're very slightly different. Like it's like cut product by something and then like one over that. But presume.
What kind of thing is that? What is the very simplest case of this?
Yeah, it's like so in the simplest non-trivial case where we take Q is equal to a point, then beta is equal to like plus or minus swap, and then we're going to get like times the product over I goes from 1 to D, and then we're going to take the degree D prime component. So we want the braiding in the D and D prime factor. So I goes from 1 up to D, J goes from 1 up to D prime. And we're going to get like xi minus xj minus h bar over. And then if we want to switch, it's going to be like xj minus xi minus h bar. Times, yeah, so up to some sign, we get this just ratio of rational functions in h bar. So it's just some rational function, which is more or less the diagonal part of the R matrix. So if you take, the normalization factor of stable envelopes, it's like Euler class of normal bundle. And then we have stab inverse. We also get denominators, Euler class of normal bundle. Just those localization factors are what we're keeping track of. But I don't think it's the same thing as its inverse. It's like, No, they cancel at h bar is 0. Then it does, yeah. Yeah, so it cancels at h bar is equal to 0, and then everything sort of becomes trivial, and you just get this commutative, co-commutative thing. But it's some like mild h bar deformation of that.
But it's only this torus.
That's causing the non-commutativity, yeah. It's just the torus in this case, which is why we care about it. Yeah, and then so, yeah, I think you really don't want to think of it as coming from a lattice model. It's like some highly degenerate, like infinite slope limit is what's coming from a lattice model. Yeah, this is some sort of funny degeneration. Cool. So that's basically the story that we want to generalize. And our goal is to generalize to classical type gauge groups.
Define this tensor product on the category C of lambda, and lambda is itself the cohomology.
Lambda is not quite a coha. It's the universal tautological ring. So it's the thing that acts by it's the like universal thing that acts by coproduct. On like MD, we have bundles, like tautological bundles, VI that live over MD for each vertex. And lambda is just generated by the operations of cup product by tautological classes of VI.
What's that? Freely generated?
Yeah, freely generated by the cup product by tautological classes. So it's a.
Why do we take this?
So really we want the braiding is given by a certain like element in here, so some sort of natural element. That's sort of naturally the CoHA is an algebra structure here, so the CoHA product and coproduct are actually linear over the tensor product map in this category. It's just the sort of the right category to consider.
Something the most universal way to construct this algebra structure, or what is it?
Another thing that might help you to think about is, so the CoHA we've written as like the positive half of a triangular decomposition. Lambda is the like middle part of the triangular decomposition.
Is it quotient or something of this universal thing?
No, I think lambda we want to actually be, so that in a particular representation we'll see a quotient, but another way of thinking of lambda is going to be like the universal enveloping algebra of loops into H, or rather like, by passing to an associated graded, which I think doesn't do so much here, we get loops into H, where in these cases of interest, the Mollick-Cocoon-Yangian is equal to like y minus, or we'll write it as, y of n of u, or y of n minus tensor y of h, tensor y of n plus. And then this is kind of like the dual of the CoHA. So, we hope to have a triangular pairing between these, and then we're going to get lambda in the middle, and then we're going to get the CoHA. And we want all this to be compatible, so we want the CoHA, the upper triangular part, to be like an algebra in modules for the diagonal part of a triangular decomposition. But I think this statement's exactly true, that if you take lambda, the actual universal ring generated by tautological classes, that's kind of like the loop Cartan part. yeah, CoHA is a module over lambda, which is like the adjunction action of like the Cartan algebra on the positive half, or like loops of this thing. And then the algebra structure is compatible with this. Cool. Yeah, so let's try to generalize this story to classical type gauge groups. And the kind of key idea is that we'll replace like parabolic induction along, here we're going to have some GLD prime, which are classical type stabilizers of some quiver representations. Our Ext complex, its stabilizer is this parabolic, whose Levi is GLD times D prime. And it's sitting inside stabilizers of the sort of larger thing we get on the other side of CoHA multiplication. We want to replace this by some GLD. So we're going to have GK. We're going to have a different parabolic. And then here we're going to have G of K plus 2D, where G K is some classical type gauge group. So it's either SP2K or it's O of some L. And these parabolics, if you think of their associated subdiagrams of a given Dynkin diagram, we have a length D chain, a length D prime chain. And here we're going to get something like a classical type chain. And here we have GK. And then this part corresponds to GLD. And we want to think of like kind of constructing a module via parabolic induction where our algebra kind of concatenates the Dynkin diagrams of type A gauge groups into a line. And here our gauge group is some sort of classical type. And those always come in families where we have a long tail sticking out. We can sort of get a module structure by throwing things onto that end and attaching.
What is the geometric sign of multiplied quivers?
Yeah, so up to localization, they're kind of, they're given by correspondences that have the same class in cohomology up to localization vectors. So I think I can explain, yeah, our proof for, yeah, why our,
I agree you don't have to prove it in the sense that you prove that the co-product is a co-product, whatever they're going to do. But yeah, why is it true?
yeah, or you do the shuffle. So in our paper for this generalization, we have kind of two proofs which reflect the sort of two proofs of the classical CoHA story. So both the left-hand side and the right-hand side, so these two things, these are given by the action of correspondences whose cohomology class is, so correspondence is Z1 and Z2, the like class of Z1 is equal to the class of Z2 times this localization factor. And that localization factor is exactly given by the braiding that we need to get the cohomology to agree.
How do you know how to compute that class of correspondence? Someone else already computed for me the class of correspondence multiplication and the class of correspondence co-multiplication. How do you know from Drinfeld or somewhere else how to compose those classes? How do you know the cohomology agrees with the gray and X alpha? Is that the proof, or is the proof there's some geometry of what the composition of these correspondences look like? Look at it and see.
It's the second thing, yeah. So it's a much more, yeah. So the idea is that on the left hand side, so Z1, we'll write our correspondence as a set, but really there's an underlying stack, and we want to think of them as extensions. So we have A going to C going to B. And together with a splitting of the central term. So here we have C1 direct sum C2. Yeah, this corresponds to, we have A1 and A2, and we multiply those to get an extension. And then going back the other way, we're sort of splitting our extension into sort of two separate pieces, finding all the different ways of breaking it up. We're only doing things up to localization calculations. And so, yeah, we're calculating at fixed points where our extension is 0. So our right-hand side, Z2, this consists of, well, we're going to take a coproduct of A1 and a coproduct of A2. And so we want to think of this as we take A as a direct sum, A1 direct sum A2. B, likewise, we're taking its coproduct. So we're thinking of all the ways of writing it as a direct sum, B1 direct sum B2. And then we're extending each pair. So we get an extension on each pair, C2, C1. Of course, if we just take the direct sum of the corresponding things, we get a direct sum of those. And these agree after localization factors. So agree up to the, like, you know, all of the cohomology classes, all that matters is what happens on the fixed points where everything is direct sums. And then somehow all you have to keep track of is the normal bundles of those loci. It turns out everything cancels, and what you pick up is precisely the braiding. And you can kind of see that the braiding is the type of extra normal bundle factor that you would pick up these two things. Right, and then so this is somehow much more general than if you already know Drinfeld is written down a coproduct. It works whenever you have the algebra, coalgebra, and they're both, yeah, defined on the same space. And right, and then so that's what allows us to sort of generalize this argument in classical types, is that there is this kind of neat geometric reason for it. Cool. So yeah, how are we going to generalize this to classical groups? And our kind of main technique is to write the stack of objects with classical stabilizer as a homotopy fixed point. So a lot of people are familiar with the notion of homotopy fixed points if they've ever done anything equivariant. So a homotopy fixed point under a group action in some stack, I just want to think of as an equivariant object. So an informal definition, which is the right thing. So an object of M gamma is the set of gamma equivariant objects in M. So unlike in the case of spaces, fixed points is the additional structure of something gamma equivariant. And this gives us some kind of fun examples. So let's take M is just the stack of finite dimensional vector spaces, by which we mean just like EGL, well, union over all D, BGLD. It's the stabilizer of a vector space of dimension D. Then if we take Z mod 2Z, this acts on M by a vector space maps to its dual. This uplifts to an action of the stack. Then what is M Z mod 2Z? M Z mod 2Z is the set of orthogonal vector spaces. So it's the set of V pairs V omega, such that V is finite dimensional, and this is non-degenerate and symmetric. It's a groupoid, right? Yeah, because its objects are vector spaces, and its morphisms are isomorphisms of vector spaces. And then we dualize, we get dual operations on all of our maps. For the groupoid, we actually want to take like the inverse push forward. So the uplift to M is a little bit funny because we want. Mm-hmm. Yeah, and so really properly we want to write an isomorphism. If we have an isomorphism phi that goes from V1 to V2, we want like, write this as gamma. Gamma push forward of phi is actually going to be the transpose map inverse, because we want it to actually be an isomorphism of the category rather than the opposite one. And then this has the property that when we take fixed points, what are we going to get? Well, we need a Z mod 2Z equivariant structure on our vector space, which is an isomorphism of our vector space with its dual. That it needs to be non-degenerate, so it needs to be an isomorphism. So our objects are equal to pairs V and eta, where eta is an isomorphism from V to gamma V, which means isomorphism from V to V dual. And then we also wanted to satisfy cocycle. Which says that like eta adjoint inverse is equal to eta, which means we're going to get a orthogonal instead of just an isomorphism of a dual. Well, we need, because it's gamma push forward of eta composed with eta needs to be equal to the action of 1 on the vector space, needs to be ID. And then it's, yeah, like transpose inverse transposed with eta. Transpose inverse is then going to be this adjoint map. Let's see. Eta, gamma push forward of eta. Gamma push forward of eta, it's actually just precisely the definition of the adjoint with respect to the pairing. Yeah, so we get this isomorphism of our cocycle condition. And then, that gives rise to this, which is equivalent to our pairing being orthogonal. The cocycle condition, it's just the usual notion of a gamma equivariant object, so it's sort of from the definition of what.
But in this case, it sounds like.
You need there's this so I've sort of elided, I've made the identification of V with its double dual in kind of the usual way compatible with your tensor product on vector spaces. There I'm actually making a choice, yeah. So I'm using the usual braiding structure, which somehow secretly is what gives rise to this identification. There's kind of another choice which is kind of fun, so let's actually modify this. If we take a different identification, so we take plus minus, where we're starting with the category of super vector spaces, which is vector spaces together with a splitting into its even and odd part, and then you use this other isomorphism from its double dual corresponding to the supersymmetric braiding, then our group action acts by parity on that, and then our cocycle condition is that the Z-mod 2 Z fixed points are supersymmetric pairings, which are symplectic on the odd part of the cohomology. Oh, yeah, sorry, yeah, that's the gamma push forward. Right, yeah, this is plus minus. And then the cocycle, the identification of double dual that gives us an action on the stack with V's, plus minus the usual isomorphism. So to get the, to get an actual action on the stack of vector spaces, we need to identify the double dual of vector space with itself. We can either do that in the dumb way that you would want, which is the usual identification with this double dual, or we could act by, plus one on the even space or minus one on the odd space. And then the cocycle condition, the sign carries over and gives you this. And then, we can uplift this to quiver representations. So given theta, which is an involution from Q to its opposite quiver, so for example, we might take this linear quiver, and we want an involutive isomorphism onto it with its opposite. So we'll go here, 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 here. Then Z mod 2Z acts on rep Q via the duality map composed with theta pullback. So we change our representation via the map of the opposite, then we dualize and it switches all of our arrows around. Q is not a doubled quiver yet. Yeah, Q is just actually the finite quiver. Yeah. Where our anti-involution sends us. So.
What is your math to Q up? What is it? Yeah, it's yellow. So that's the other one, yeah. It's not, did you call it evolutive because
you square it, you kind of get back to where you started. Q up, you push forward, and like I get to Q. You go from here, and then you go back to here, and then.
Yeah, previously you were talking about some.
Yeah.
What's the relation?
Yeah. So. In the preprojective case, it's easy to construct an anti-involution on a preprojective quiver just by sending each arrow to its double its opposite one. If we want actual representations, so another kind of example is when A is equal to pi q mod, then we can take theta, which is on a representation of the double anti-involution of the doubled quiver. It's its opposite. And then we want the pullback along, we'll call this operation tau. We want tau pullback of the symplectic form to equal the symplectic form. Then if we do this, m z mod 2z carries symplectic form. But it's a non-trivial condition on the involution. Actually, in order to arrange it, we generally need to modify tau by a sign. And so one way to arrange there's a bunch of choices. That's one of the choices, is you sort of swap the two arrows. But it only works if your quiver is bipartite. Is if Q is bipartite. And then, yeah, vertice, and there's no arrows between things in one particular part. And then in the doubled quiver, we're going to get kind of arrows that go back. And then we assign these to be like odd and these to be even.
You can surely also define such theta, for example, for the extended AN quiver, right? But just mirroring everything. So
mirroring the two and switch, yeah. So you just always need this condition, and you can also arrange that with a sign. For the affine AN quiver, yeah, there's also this folding. But yeah, the point is that you can't always get compatibility with the symplectic form. So you need some sort of condition like bipartite. So for example, the space of maps, so hom from an orthogonal vector space to a symplectic vector space is itself symplectic via this construction. But there's no obvious way to get a symplectic structure on maps from something symplectic to something symplectic or the other way, or analogously with orthogonal. And the way you want to do this is you want to yeah, start with some sort of quiver, write down the natural symplectic form on its doubled quiver, and then you need your involution to have signs arranged in such a way that the involution pulls back the symplectic form to itself. So it's some sort of funny condition. Yeah, so in the end, we actually get, in this case, we get these orthosymplectic quivers as fixed points. So in the end, we get orthosymplectic quivers as z mod 2z. So if we take this thing with as some sort of fixed point, I think it's a good one because at least it fits naturally from the perspective of cohas, is that it's like a z mod 2z fixed point under a kind of dualizing like anti-involution on the quiver representation. So this gives rise to a quiver where here we're going to have either an orthogonal or a symplectic type gauge group. And then here we're going to have our usual D. And then here we have these 1, K1, 2, D3. So these orthosymplectic quivers, we're going to have M z mod 2z in some invariant degree, so some degree D can be written as mu inverse of 0 for this classical type gauge group by GL times GL D2 times GL D3. And in some cases, so in these cases, when you have a vector space with a group action, you can write the fixed points as like the fixed points of the underlying vector space quotient by the fixed points of the group. And this is some sort of cotangent version of that where you also are taking the part of the cotangent stack, which is this moment map direction, and we sort of get fixed points of the entire cotangent complex, which means we're taking the moment map for this actual fixed group. Sort of makes sense that something like this would be the case. And so how do we get CoHA modules is we literally just take fixed points of the CoHA correspondence. So what was the CoHA? The original quiver, yeah. So the main construction is that's where we're kind of doing that right now. Yeah, we're saying that so we can get this GK as the fixed point stabilizer of one of these fixed point objects. And the way we're going to do this parabolic induction diagram to get the CoHA module multiplication is just taking fixed points of a 3-step CoHA correspondence. CoHA of the original quiver, or pre-projective algebra, the original unfolded thing. So we start with M goes to M goes to M. We have this thing, tried as SES3, which is the convolution of SES with SES. So that gives us like the double multiplication map to M. And then we're going to take Z mod 2Z fixed points of this entire diagram. And where, yeah, so it acts on SES3. Because it's like 3-term, you know, maybe SES3 isn't a great name. It's well used in the paper, but you can think of it as like, you know, the composition of 2 short exact sequences, and so you have a filtration of an object with 2 sub-objects. So you kind of see the 3 there. It's actually kind of length 5, because then you have the quotients. But SES5 looks worse on the page than SES3, so we use 3. Yeah, and so we're going to call the fixed points SES OSP for orthosymplectic. But it's composition squared, so it's like, it's the fiber product over the middle base, yeah.
Product.
Yeah. I'm going to keep calling it that, but...
I think about this as an object with that
with 0 goes to A1, goes to A2, goes to that. And I'll draw it in a sec, which makes it kind of obvious what its fixed points are too. Yeah, so...
but it is like multiply second 2 guys and multiply those.
Yeah, literally, yeah, we multiply those and multiply those. And then that's given by this convolution, because that's sort of how composition of operations work. So this, our gamma action sort of switches, it dualizes everything, so it switches the order. And so the middle term gets sent to itself. So our fixed points in the middle, we're going to call the fixed points of the correspondence SES OSP. The largest thing is obviously the center, and so that gets sent to itself. So our fixed points end up looking like this, where we've defined SES OSP via this fixed point construction. So this is actually just a geometric thing. So it's because the fixed points isn't a Cartesian pullback. It's not like you can start with the CoHA and get a module that way. Here you actually have to take the geometric thing to get a module. So it's not an algebra. There really is geometric input here. Folding. One way is to take a framed quiver. So a coha, if you have that your quiver as a sub-quiver of something else, then you know the coha is like a sub-algebra, and so it acts on the larger algebra. And so one way is like it acts on Nakajima quiver varieties by basically this construction. If it preserves stability conditions, then you know you get an action on the representations of a larger quiver with extra nodes and arrows. So that's the usual sort of way that people think of coha representations as related to Nakajima quiver varieties or something. Yeah, this is a different construction of modules. So it's, yeah, there's various other ways. So some people in this room like to study the representations on quasi-maps to Nakajima quiver varieties. You can also get a representation there. So there's all sorts of ways. So it's some kind of universal algebra that has lots of different constructions of representations. And I'm proposing a kind of one that I find interesting. Right, so we can think of SES composed with SES. The nicest way to write it that makes the group action obvious is, well, we start with our first short exact sequence. So we'll write this as the kernel of something, and that goes to B. And then we have an extension whose sub-object is that, whose larger object is A. We'll call this A2. And then we can like fill in the rest of the diagram like this. So this is A1 is our first object on the left-hand side. A2 is our last object on the right-hand side. B is this object in the middle. So we take an extension of B by A. Then we take an extension of A2 by B. We compose this to get this largest object C. And then its fixed points act kind of diagonally along this line. And so our fixed points are going to correspond to, here we have some A, here we have some A, here we're going to have C, we're going to have B, where C and B now are actual homotopy fixed points, which means we have an isomorphism of the reflection across this line. So here we have a map, and then here we have tau applied to kernel. This is tau applied to A, which is equal to tau applied to A. And so we can think of A to C is an isotropic subobject. And then B is equal to the orthogonal complement of A mod A. So we're kind of doing some sort of funny classical type extension of B by A and getting C, where we're adding A plus A dual. So as vector spaces, it's just the co-kernel of the map to T, and then it's the co-kernel of the map from A1 to C. I mean, we're taking like the composition of two of these short exact sequence correspondences. Its data is kind of represented by all of these objects. And then we're taking Z mod 2 Z fixed points that acts by exchanging the first and three factors and dualizing the middle factor over here and the thing on the right-hand side. And then I'm just writing down. Well, action on SES3. Well, I'm telling you how to act on SES3. It's like SES3 consists of this data, and then the action we're just sort of folding. Yeah, defining the action this way. By taking the reflection with tau along this, we have to dualize the objects here in all of the corresponding maps. Kernel gets switched for the tau of co-kernel, A1 gets switched to tau of A2. Yeah, 0, V1, V2, and then our vector space, yeah. Yeah, so if we have 0, V1, V2, and then we'll just call this whole thing V. This, we want to send it to, so A1 is our smallest subobject. Okay, well, let's further, yeah, well, this is V, and then we get surjections onto V modulo V1, and then a surjection onto V modulo V2. And then we're dualizing this map, right? So we get V modulo V2 dual goes to V mod V1 dual, goes to V dual, and then these surject onto V2 dual and V1 dual. And from the perspective of flags, it's kind of well known that the fixed points of these are going to be like isotropic flags of half the length. So we're just forcing V1 to be isotropic and V2 to be V1 perp. And yeah, that's actually exactly it. Yeah. So our fixed points are 0, sitting inside of V1, sitting inside of V1 perp, sitting inside of V. The fact that V1 sits inside of V1 perp means that V is isotropic, which is why you're going to get this subobject has to be isotropic with respect to pairing. And then this other sort of weird middle extension thing is just V1 perp modulo V1. In this abstract language of an object with an isomorphism with its dual, it's one that when you restrict to the map on A, the pairing is 0. So the induced pairing on the subobject is the 0 map.
So this is actually your, this is that object. Can I think about symplectic pairing? So the symmetric.
For a vector space, yeah, we saw that the fixed points, Z-mod 2Z fixed points of vector spaces is a vector space together with an orthogonal or symplectic pairing, depending on signs. Yeah, because if we take, so V itself, if the whole thing is fixed, that means if we have a term in the sequence that's fixed, we need an isomorphism of that with its dual, which is a stacky fixed point, one of these homotopy fixed points. And so that gives us a pairing here, and then we can induce the pairing on a subobject, and we want it to be 0. It's just a symmetric pairing with a an odd vector space. Right. So now I guess it's time to state the main theorem. This is let's give these maps names. So I'm going to call that map capital P, and I'll call that map capital Q, which is then in some of these contexts that we've discussed. So we have a different version of the theorem for CoHA of a quiver, pre-projective algebra, quiver with potential, some geometric situations. Cohomology of M tau is a tau twisted Yetter-Drinfeld module for the cohomology of M under, we're going to have an action map which is going to be P pullback composed with Q push forward. And then maybe we want to do plus or minus signs to match with other stuff. And then we're also going to have this thing called delta tau, which is just going the opposite way. We take Q pullback, P push forward, and we're going to take, again, some sort of funny sign. Here we don't want to swap, actually. Again, we have to localize because the coproduct isn't so well defined. And that is the main theorem. So this goes from cohomology of M, tensor cohomology of M tau, goes to cohomology of M tau, and this goes the other way. What I want to explain to you is sort of what is this like action-coaction compatibility between the two. So the tau-twisted Yetter-Drinfeld module, this is a notion that we couldn't quite find in the literature, so we just kind of came up with it because it looks kind of close to the notion of a Yetter-Drinfeld module, and it reduces to that in a special case.
Sorry, you want this guy to correspond to the Youngian?
It's
Or you're doing something else?
something else, yeah. It's
why didn't you think of the Youngian?
So we thought about trying to. It's closer to a twisted Yangian. So the current state of our knowledge is that. So if you take the Langland's dual of the Yangian of a non-simply list group, this is going to be a twisted Yangian. The same way that because this is like an affine Lie algebra and its Langland's dual is. If you take an affine Lie algebra, its Langland's dual is some sort of twisted algebra. Why couldn't, I mean, we just found this construction and, it doesn't actually seem to be the Yangian of a non-simply less group. It just, doesn't seem to be an algebra that acts.
So you need a different power.
Yeah, so I think if you take tau that doesn't kind of dualize everything, probably you can get a Yangian of non-simply based. Yeah, that's right. If you want a Yangian of something non-simply laced, yeah. Yeah, so
it sounds more like you're saying the Yangian of an ordinary APU thing is going to act on, hold it up.
The positive half, yeah. So the doubling is sort of funny here because somehow we're starting with the positive half of the Yangian of the unfolded thing, and then some quotient of this has a Verma module, which is this thing. And so it's actually, so it's not Yangian of something like non-simply laced. It also doesn't seem to be the twisted Yangian of something. It's like a dual, it's rather than being a subalgebra of like even loops or like fixed point subalgebra or some sort of quantization, it's almost like the quotient by the left radical of a fixed point subalgebra. I'll maybe explain some sort of conjectures about what it's supposed to be, but a lot of it's pretty wide open as to what's sort of going on. The one sort of important step to try to understand how the doubling interacts with this whole story is precisely this tau-twisted Yetter-Drinfeld condition. So that's an ingredient that certainly if you're trying to understand relationship with Yangian, you need to understand this condition better. And we couldn't find an attestation of this notion in the literature. So tau-twisted YD module is a condition in braided module category. Which we'll call curly D. And the idea is we have, in this case, D is something like lambda Z mod 2 Z fixed points modules. And we have box tensor, which is a map from C tensor D to D, which we write as diagrams. We had objects in D as thick lines and objects in C as thin lines. And then we also have this map kappa, which is a natural transformation from the box tensor to itself, which we write as like a BC type braid, satisfying the like Cherednik reflection equation or a BC type braid group relation of the form like beta kappa is equal to kappa beta. And we can talk about module and co-module objects in braided module categories exactly as you would expect. So we would have module structure is our action, co-module structure is our co-action. And this twisted Yetter-Drinfeld condition yeah, actually the category, so our thin strands is our braided monoidal category. So those are thin strands, just like we talked about before. Our box is maybe some fixed object in D. And our box tensor lets it take a thin strand and a thick strand and put them next to each other. And that's our tensor product. Kappa is a morphism, so on objects, which can be written as the product of these two things, means we can write it as a product, a thin strand next to a thick strand. We get a natural transformation, which gives us a morphism on every object of that type. And we want that to just be some satisfied, like, it's a natural transformation, and it satisfies some axioms that give us the type BC braid relations. And yeah, so in this case, right, and then we have an action and a co-action, which we think of as, suppose we have an algebra object in C, a module object in D. Yeah, I draw the operations in terms of the pictures, right? Because we can take something in A and something in M to the product, to the coproduct otherwise. And yeah, it's the universal tautological ring, but you only take like those that are fixed under taking a dual.
This thing you've written down as a definition of what is graded module category.
Yeah.
So what is the solution? How is that related to lambda C modules?
That's the definition of the category. So D is our.
You're saying that if I remember from before, it was C with lambda modules.
Mm-hmm.
Give some graded tensor structure on lambda modules.
Uh-huh.
You're saying this is the definition of graded module category, and moreover, this D graded module category. That's
Yeah.
formula which is not
right. Yeah, that's right. Yeah, it's the same formula, just with duals. Yeah, you fix points of the previous formula. We just take representations of the fixed point algebra. And then, so M is a tau twisted Yetter-Drinfeld module if the following two diagrams equal to each other. So if we multiply and then we co-multiply, or act and then co-act, we want this to be equal to the diagram we get if we take a triple tensor product. We want to flip this around this way, go underneath, and have all of these strands match with each other like this. So yeah, on the left-hand side, we just have multiply by co-multiply. So, this is act composed with co-act. And on the right-hand side, we have some sort of complicated expression. Literally that picture, yeah. Literally, like, we co-multiply 3 times. We do a bunch of these braidings and the reflections, and then we co-act here and act here. And then we multiply the sort of 3 things left over at the end. From top to bottom, yeah. So action is from top to bottom, co-action, we sort of split them off at the bottom. And so this is some kind of, horribly nasty expression in the...
Just so I remember, like C was just a lambda module,
Mm-hmm.
and D was
Mm-hmm.
lambda was that.
Yeah, so if you only have one vertex, so Q is equal to a point, lambda is K joined infinite sets of variables, which are symmetric, and lambda Z mod 2Z are just, we want symmetric variables in the same thing under Z mod 2Z that sends everything to its inverse. So this is polynomials in x1 squared, x2 squared, and so on. Negative 1. So in the of the CoHA, for the CoHA, cohomology of M.
How does cohomology appear?
It's the thin strand, yeah. So here, our object here is the cohomology of M, and here we have the cohomology of fixed points.
So the multiplication and co-multiplication, those are specific algebra objects.
The algebra object are multiplication and co-multiplication. So when you have a thin strand and something's happening, that's a multiplication. When you have something's happening with a thick strand, you use the action and coaction. Those are action and coaction are written here. It's the push-pull by the fixed point SES-OSP correspondence. For a braided module category. Mm-hmm.
What does that mean? Every time you have an algebra.
And then you could talk about an algebra object and a module object. Algebra object is in C, module object is in D.
That delta you wrote there. What is delta over here in this picture?
Yeah.
The strand ending on a fixed strand.
Yeah.
Is that something about C and D or about specific algebra object and module object?
Algebra object in C. Yeah, so this is we start with here we have A is an algebra object, M is a module object. Here we have M, A, and M. So we always have this braided module category is just the data of these things. So this gives us braided module category. And we can take a tensor product for this thing. And this is like A in C is algebra object. And M in D is a module object. Yeah. Module object, co-module object. And then something satisfies this tau-twisted Yetter-Drinfeld condition is if when you compose these, you get this correspondence.
So what's the result of these things? The whole
of just a module? The usual Yetter-Drinfeld module, so without twisting. So when tau is actually equal to the antipode, and like kappa is trivial. Well, kappa is actually equal to just tau tensor the identity. So when we braid around, we just act by the antipode in a Hopf algebra object. So A is Hopf algebra object. Then tau twisted Yetter-Drinfeld is equivalent to like a left-left Yetter-Drinfeld module, which is also equivalent by a result of Majid to a module for the Drinfeld double of the algebra. So this is equal to a dual tensor A module. The point is that what the Yetter-Drinfeld condition does is it lets us sort of normal ordered when we multiply and co-multiply in the wrong way, where co-multiplication corresponds to more or less multiplication by the dual algebra. And so what our condition here does is it lets us normal ordered the multiplication and co-multiplication and form some twisted version of a Drinfeld double. So it gives rise to, we can naively define double tau of A to be equal to some formal A dual tensor A, where this diagram is going to let us normal ordered. So if we write the coaction of A is an implicit summation of A1 and tensor A2, we can write like B tensor A for B and A, and well, I'll write it as capital. Maybe that needs to be capital for an element. A1 tensor A2, B tensor A, where B is in our algebra here, and A is in the dual, we want to write this as an expression which is normally ordered. So this is something like the pairing of B1 with A1. Here we have A2 tensor, multiplication of these is multiplication A2 tensor B2, and then here we have the pairing of B3 with tau of A3. And so you can formally define some sort of twisted Drinfeld double in this braided module category. And this Yetter-Drinfeld module condition sort of tells you how to normal order the positive and negative halves of this kind of funny double algebra. Huge open question, like in this context where we have this nice Yangian description of the quiver, like what is the actual algebra that you get by this construction? We have a shuffle algebra formula, but identifying with a Yangian is, or a twisted Yangian or a dual, it's not so clear exactly what that's supposed to be. Yeah, there's more examples or things where I could answer any sort of questions after this, but this is the main theorem of the paper.